So we are ready for day 2 and a new session on fission fragment properties, which is promising to be very, very interesting. So our first speaker of the day is Antoine Lemasson, and so little short bio. Antoine received his PhD in 2010 from Ganil on the interplay between nuclear structure and reaction mechanism in exotic Borromean nuclei. Between 2010 and 2012, he did a postdoc at MSU on measurement of collective properties of N equals Z nuclei by lifetime measurement. And since then, 2012 to 2023, I don't know what he's doing now, I guess. He's a balanced scientific coordinator with research activities covering nuclear structure and fission dynamics using fission-induced inverse kinematics. So, please.
I'll take this one, no? Okay, yeah, I will adjust as well. Okay, thank you. So I'm very happy today to try to give you an overview of the fission fragment properties and also what are all the challenges associated to measuring fission fragments, and especially in this place. So I warmly thank the school organizers for making me work on this. But it was really fun, so I will try to share with you what I went through. So this is the outline, so I hope I will manage to go through, but in any case, the idea is to give an overview of all the measurements that are trying to measure as precisely as possible the various aspects of the fission fragment properties and their observables, and I will go through, but I could not really, I had someone to get back to this. Luckily, yesterday somebody did a lot of work for me, so I will go through this very quickly, but we have the first stage that you form the fissioning system, so I will not discuss this part, but basically you have your fissioning system with a given, let's say, numbers of nucleons, neutrons and protons at a given excitation energy and in a given state with J pi. So afterwards, in case the system decides to go for fission, so it will go slow an evolution, and at some point you will have the scission where the nuclei get deformed, and then you have these two kind of pre-fragments that are appearing with that I will call A and Z with star, means before getting any kind of modification or evaporations. That are the forthcoming steps. So when they split, then they start to get away, and they are releasing the excitation energy that they have, first by evaporating neutrons, and later on by releasing by prompt gamma rays emissions. On a longer time scales, of course, you will have then the decays of these fission fragments. And you can see that the time scales are very ranging from zeptoseconds to, let's say, very long mega years. So experimental techniques have to cover this. What are the observables? Basically, in this part of the fragments. So I don't speak about the entrance part, which was covered yesterday, but here we are discussing about how the configurations are of the systems when it will split, or kind of pre-evaporation fission yields and velocities. After evaporation, you have independent fission yields, either as a function of mass or isotopic ones. Kinetic energies, velocities, neutron evaporation, gamma ray multiplicities. I will cover some of them. Some of them will be better covered in the Thursday talks and lectures, but everything is naturally interconnected, so it's nice that you will see how they are connected. And they are cumulative yields, so I will not that much cover this part, where we have a talk yesterday by Guy that also already gave some information on this, and maybe we can connect at some point. So let's dive into this now. But just before this, of course I could not resist these historical aspects, but basically everything started by chemistry, no? You identified that some elements were there, and they were quite unexpected, and all the story started like this. And basically now we are like 86 years, but it's still a lot of questions that are not remains to be open, but we are now having more and more precise and varied experimental techniques, and that I think we are moving on with, let's say, very interesting questions that we have to answer, and new methods that are bringing new insights into this phenomenon. So the idea will be to go through the fission observables with a focus on selected measurements and basic quantities on the fission fragments, like energy and velocities. I will not cover angular correlations. And the fission process through the mass distribution, charge distribution, kinetic energies, the yields, the pre-neutron evaporation yields. So I could not resist to go through some historical aspects. So I will first say I want to show what are the fundamental measurements that allowed us to have some good understanding and already very overview of what is the fission process. Only by few measurements we already have a lot of information on what is happening, and I want to remind you this by the various measurements that were done in the 60s and even before. So by kinetic properties of fission fragments, energies and velocities, and fission fragment masses. And I will do everything based on a simple system, not at all simple, but let's say something that we can have relatively easily is a fission spontaneous force. It's not easy because why it's spontaneously fission is already intrinsically a good question, but experimentally it's making fission fragments available in quite an easy manner. So the spontaneous fission source of californium-252 has mostly alpha decay, but spontaneous fission for 3%, and this you can use to do, let's say, a lot of measurements of energy and velocities. So let's start from basics. So you take your spontaneous fission source. So first you have to make it will fission. Okay, nice. Now what can we do? The simplest thing is first to measure what is going out of this. So let's take a silicon detector and look at what is going on. So the first question is that, just to start easy, but we need vacuum, because from the very, very early times, we know that the ions are slow, heavy, and they do not travel basically less than, for the fastest one, 2 centimeters in the air. So if you want to do something, first you have to work on your vacuum to be sure that your fragments reach to first your measurement systems. It was just to start easy. But now let's start. What are the basic properties we can get? So you will see I based on 2 articles, this article from Schmidt and another one just after. You can go and look, they are very nice articles. You see a lot of details on all of what they have done. I really encourage you to go and have a look into this. Take 2 hours to read them, and you will learn a lot, I think, if you have not yet read them. So the first thing is that you need to measure the energy. So let's see, you measure the energy of one of the fragments. So you basically make your measurement. You will see this is what you will measure. So here this is the energy, let's say yield, percent in yield, and you see these 2 bumps. And the first feature is that basically, if you look at the total energy that is released, basically you can say that on an average, of course you have a different distribution, but basically like 185 MeV is, let's say, accessible here. So to get this, it was a very hard way, because they have to develop a very advanced calibration procedure, and if you read this article, you will see that they used bromine and iodine beams and alpha particles to calibrate your silicon detector, because you have the question of the pulse side effect. And I really encourage you to go and have a look at this. It's really impressive to see that what was done and achieved in these times. So we get the energy. Now, imagine you enhance a bit your system, and now you say you make, next to your FIESTA source, or let's say spontaneous fission source, you make an emitting foil, so that when the fragments go through, it will emit an electrons that then can be guided to a scintillator. Then you can pick up the time of the start of the time of flight, and you will have your stop by your silicon detectors. So then now you can measure the time of flight, and then in some way the velocity of the ions. So if you look now at the velocity, so this is the channel number, so this is really what you measure. And you have here the channel number, and here the time of flight, which is reversed because of the way it was done. But basically, in the end, you get your velocity profile. You have here also this double hump profile, peaking at 1 centimeter per nanosecond and 1.4 centimeter per nanosecond. So this is what you get from now. Okay, let's continue and correlate them. We are physicists, 2 parameters. Of course, we want to correlate them. So you here have the energy as a function of the time of flight. And you can really now start to separate 2 groups of ions that that are measured. So based on this, naturally, you go back to natural physics, you get the energy, and basically you can get to the mass. So you will measure the independent yields, that you can call them in this way, but basically you get the mass, basically based on the energy and the velocity measurement. So there are sorts of uncertainties here. So I said distance, okay, let's hope it is negligible because we know how to place the detectors. Velocity, imagine you have a very good system and then maybe you can get to 100 picosecond resolution over 100 nanosecond time of flight, so okay, it's relatively good. But still have maybe lied to you a bit because when the ions go through the foils, then they are not losing the same amount of energy. So we have a lot of work to do here, basically to account for the energy loss, both in the sample, where the source is, in the foils and the dilators. This is where all the challenge comes, and a lot of work was done to achieve this, and this is still a very challenging aspect of those measurements. So again, we gain new parameters. We want to correlate it with the other one. So the energy versus the mass. So here you have the average energy of the fragments as a function of the mass. So I will try in the few slides just to show you how we can quite easily account for this shape, and not maybe for all the details. I will not tell you all the detailed shape, but at least to give you a flavor how from simple principles we understand a lot about the process itself. So it's all about energy conservation and momentum conservation. So imagine you have californium-252 that splits into two fragments. So basically, if we use momentum conservation and assume, let's say, conservation of this mass, which are those hypotheses. I'm not saying that I will reproduce exactly the shape, but basically we can get back to a formulation of the energy as a function of the mass. And you can see that if you plot this, okay, it's already quite okay, just using the fact that we have the total energy, which is basically 185 MeV. This works relatively well. Let's go one step beyond. So let's use the fact that those nuclei, they are charged. So let's assume now they are touching charged spheres, and we can see what are the repulsions from this. And now we can just move on a bit and basically get a better formulation based on this. And you see that now we can already recover some good part of the shape. So you see, just by assuming that you have, here I made a spherical charged spheres, but we can change this and it will basically change what is the D here by making some, let's say, deformation, for example. So you see that just on basic principles, we can already reproduce a lot of those correlations and have an idea of what is the energy released, what is the dependence, how it goes, and which means we already have some idea of what is going on the splitting. So let's move on one step further now for new measurements. So now, imagine now you measure the velocity of the two fragments. So here is the type of setup. So this is the second paper that I encourage you to have a look. Here basically you have a sample in the middle. Let's say in this case, imagine 252 californium source. So you make an emitting foil, and here in scintillator you basically measure the, let's say, initial time, and you have two arms to measure the fragments of in coincidence of the two fragments. So if you assume that the total mass is conserved, here means there is no evaporation of neutrons before the system splits. This is basically what I mean here in this assumption. So basically here, M1 star and M2 star are what we can call before evaporation mass. And you can basically get back that basically if you measure the velocities of the two fragments, assuming that basically the emission of a neutron do not too much alter the velocity of the ion, you can basically get back from the velocities, from two velocity measurements, to the mass before evaporation. So this is also very interesting because now we have measured the mass from the basically energy and velocity. Now you have this measurement from the two velocities, you have the mass pre-evaporation, and now we want to compare them. But again, here one more time, there's a lot of work that has to be done because the velocity are changing, because when they go through the foil. So let's go one step more. So now let's, yeah.
I'm just trying to ask a question to break the ice a little bit and encourage students. So you mentioned, well, we assume that the neutrons don't take away too much. Could you please elaborate what you do about the neutrons? In the last step, you said in the last slide that you are assuming here that the neutrons aren't taking away some energy.
they take. No, I'm just saying. No, so basically the point is that imagine your fragments are a mass 80 or something like that, or mass 100. Basically, you will evaporate one neutron out of, let's say, 100. Okay, so this is basically, by this sharing, it will alter the velocity, but in this proportion. I think this it can be done precisely. It's more to give a flavor how you can get back to this. So now, of course, if you want to get this in precise way, you have to account for this evaporation. Okay? And this can be in some way computed. Okay? So, no? I thought there was a question. Okay, so let's compare now those independent measurements. So we have this post-mass measurement, and then we have in red here the pre-mass measurement that basically come from two velocity methods. So if you can we can compare them, and this is what was done at that time, and they were measured independently, and you can have some information of the let's say numbers of neutrons that are emitted by making the difference. So this was already a very interesting result that basically you have an idea of how many neutrons are evaporated independently of measuring the neutrons. Here they are all based on the mass measurements. Okay, but now to move a bit further, because now we are in the 60s. So basically, how we can get better by trying to measure those quantities at the same time. And this is what is called the 2E2V method. So I'm still quite long time back, but quite impressive result from the 80s, from ALL in Grenoble in France. Basically, the idea is that you will measure both the velocities, both the energies, and by using the various measurements that you get from the energy and the time, you can get the post-mass, the pre-evaporation mass at the same time, and recover the neutron evaporation. I just want to highlight here that if you look at what are the resolution of the mass that could be achieved at that time, basically based on the time and energy measurement, you get basically to 6 per mil, which is outstanding here. Of course, this picture is maybe misleading because here they have put Gaussian fits on the top. So basically, it's really resolved here, and you see the mass in the mass range of 100. So now, again, the main challenge here are the slow fission fragments. The fact that we want to measure several things at the same time, so the ions have to go through measuring one energy by stopping an ion. It's okay, easy. But if you want to measure basically the velocity and the total energy, you have to be transparent, but you are still altering because you measure, so you interfere with the measurements, and this is the whole challenge of those measurements, is how to account for this, so by knowing properly the energy loss, by minimizing all the dead layers. And this is basically what I want to highlight in the next part, is that the idea is that now in the 80s, everything was measured very nicely in the very small solid angle. Now if you want to get better statistics, you want to have larger solid angle coverage, larger coincidence between the fragments. And now the challenge comes because you want to have big detectors where you have good knowledge of the response of those detectors and to account for all the energy losses that are occurring. And this is basically all are those modern setups, I will call, that are presently taking data or making even new developments, Verdi, Spider here, or Falstaff in Ganil, where the idea is to increase the acceptance by having, let's say, new, or let's say, emitting foil detectors. So basically you really have thin layer, you have secondary electrons, you want to collect them, and you want to also measure the position at the same time. You put new digital electronics to try to see how well from the energy measurements you can get some information. First, high resolution of energy, but eventually can we learn something about the stopping down of the ions that is related basically to the charge of the ions. So they are very challenging measurements. And this is really what is going on today on how we are trying to move on this. The physical limits are really due to the resolution in energy loss because of the nature of the energy loss, which is a stochastic process. Basically, you have some point you cannot beat the stochasticity and the randomness of the process, and this is really one of the limiting factors. And all this relies now on the capacity to do advanced simulations of the setups. And here I highlight some results, I think, from here. where you see that there are a lot of work that is done to basically be able to map as well as possible the response of the detectors on existing, for example, fission source data, and to account for all the complexity of the response of the detecting system to the wide range of nuclei that are occurring in fission. Because maybe this I missed to tell you from the beginning, but the very challenging part of measuring fission fragments is you are measuring ions with wide range of velocities which is relatively large, range of charges, or let's say, charges which is relatively large, so that it means the response and the energy loss of the ions is really different from the heavy to the light fragments. And you have to do this at the same time, because otherwise you are biasing your estimation or measurements of the mass distribution, for example. So this is really the challenge that is going on. So those setups are basically, can both accommodate spontaneous fission source, but also neutron-induced fission source. And, okay, let me just go to see. And the point that I just want to make here is that, and this is related to what will be most likely the lecture of Thursday, but now we are interested in those independent fission yields, which are some real measurements of what is being produced in the end. But from the, let's say, fundamental aspects, we want to know how we went there. And we really need to get back to what was at the session. And this is really a challenging aspect, is that we want now to be able to get back to this, and that's what, of course, now measuring the pre-evaporation mass is really challenging. From long time back, it was measured, those neutron multiplicity as a function of the mass was measured independently, for example, and you will see it on Thursday. You can measure those quantities. You can eventually apply them independently to the independent mass yields that are measured, and you have now to try to see how you fold what you get in mass here, because mass is not exactly the same as identifying a nuclei in Z and A. Or you can measure independently, let's say, correlated way by the 2E method, but you are somehow limited by the velocity resolution. So this is the two different approaches, but what I just want to stress here is that basically trying to get back to those pre-evaporation mass distribution is really what will now constrain the way we can model the system. Yeah.
What's like the time scale of neutron evaporation? I guess the What's the time scale of neutron evaporation? And I guess the follow-on question is, what's the application of knowing the pre-evaporation yields? Because I would imagine it happens pretty fast, in which case
so
seems like you mostly care about the post-evaporation yield.
Yeah, this is a matter of taste. No, so let me clarify this. So evaporation scale is 10 to the minus 21 or something like that. So of course, non-measurable from, let's say, non-separable from direct measurements, but we can do it by indirect measurements. Now, what is the interest of this? The interest of this, I mean, for example, my interest in this is that I would like to see how we are able to basically reproduce or model the way a system like Californium-252 is fissioning. So the evaporation basically is related to the excitation energy that will be given to the fission fragment. So it's really related basically to how the system has evolved, how the excitation energy has been shared between the system. And this, I mean, we need to know this information to be able to, let's say, understand whether the modeling is correct. I mean, are we properly sharing? Should we consider this all uniform? We share as a function of mass, we share as a function of Z, I don't know. But this is the question. And if we want at some point to reproduce this, we have to get this information. So this is the motivation. Let's say, if you want to use it as a data for putting as an input to something that you want to say, okay, I have those fissions that will come with this fraction, of course, it's not so important. Nevertheless, I mean, the energies of the neutrons will depend from where they come. Huh? So this will not so, you still need this information. Okay. So maybe a small, let's say, step on the side is that what have we learned from those simple measurements? I mean, simple, not so simple, huh? They are really fundamentals. So we measure the energy and the velocities, and we learned a lot about the physics of the fission. So I will focus on, let's say, maybe slightly older measurements. From the 70s, it was already known that basically from measuring in different systems here, uranium to Einsteinium, that you change quite a lot the system in numbers of components. But if you looked at the mass yields, basically you see kind of stability in the heavy fragment peak. So this was done basically by measurements of this type. Huh? It was not requiring more. And this highlights the stabilization of those heavy mass. That is highlighting that some specific configurations are mattering in the way the system is splitting. Okay? If you go slightly more advanced, basically now you have the mass, but you correlate with the total kinetic energy here. So total kinetic energy is a function of mass. And you see now that you start to have some different locus, because basically if you have the total mass, okay, you see two bumps, okay? If you have not too much imagination, you make two Gaussians. Okay, maybe you want to have more imagination and start to say that the system is slightly more complex in the way it is evolving. It's not just splitting in an average by having this. And maybe there is more way of splitting. And the total kinetic energy basically gives you those kind of information. I remind you that when I showed that the total kinetic energy dependence as a function of mass, we can already start to put some idea about the configuration at the session. What are the shapes, how the systems can be, how the two fragments are separated. And this is those kind of information that somehow were used in some way to develop some way of seeing the fission, the fission as different fission modes. Basically, that are somehow following some, let's say, structural effects or shell effects. When the way the system is evolving, basically, they are affected by specific configuration of the system in its evolution and are favoring energetically, for example, the way how the system will evolve. Okay? So already based on all those measurements, a lot we have learned on how the fission occurs. And this is what I just wanting to make this point here. So from these very simple measurements, okay, let me see where I am. So now, okay. So from these very simple measurements, we can go to a lot of more types of measurements. So because the techniques are the same for most of the neutron-induced fission experiments. And basically when you can get the total kinetic energies, you can try to get this post and pre-mass evaporation mass distribution and yields. You can apply it to neutron-induced fission, but also to fusion fission or fission that is populated in systems which are slightly more excited, but basically it is the same, because you can measure the two fragments and get back to some information. Of course, now you can start the question, is there some evaporation before, because my system is more hot? But still, those measurements apply the techniques, the complexity, all the challenges of measuring getting back properly to the total energy, to the proper velocities. So here I just highlight that in those neutron measurements, I mean, there are a lot of several facilities that now are, let's say, in line or already producing data for those in different energy scales of the systems, and where you have different energy range and different flux, and this was shown already yesterday. So now with this we can measure a lot of systems. Huh? Basically, as soon as you can make a target, a fissile target, or let's say a system that you can, even with high energy neutrons, you can make fission systems that are not even fissile. So now we can do a lot of this, but you still are somehow, you have a big advantage because neutrons can be well defined in energy of the system you are populated, but you are limiting by the targets that you can basically produce to measure this. They are complex because you have to prepare the samples, so we saw already yesterday all the complexity associated to preparing the samples. So one way to go around this is to try to populate the system in a different manner. So of course there are some questions associated to this, is that how can we produce the system in a similar, or I would never say same, but similar conditions. And this is what is kind of called the surrogate method, is that basically you try to populate a system that will fission by a different entrance channel than having a neutron capture. And I think there is also a lot of interest today to see how well, I mean, how different are the properties of the fission fragments that we are measuring, and how the fission has undergone a different way because the system was populated in a different, let's say, entrance channel. So the advantage of this is that if you look now at the map of nuclei, so this is already quite old, but you see that now basically most of the blue dots, not all, but were spontaneous fission or particle induced, let's say neutron induced. But now you can produce a lot of other systems by different reaction mechanism, and you can try to see how the things are changing, because we know that basically the structure of the nuclei is affecting the way it will fission. So let's try to see to change how the composition of the system, and to see if we can basically pinpoint some different structural effects. So this is one of the motivations that can be. So here in this presentation, I will not too much discuss, or even not discuss, the fusion fission. One of the main challenges of fusion fission is that when you populate your system, you do it basically at Coulomb-Barry energies. And depending on the energetics, basically you will most likely populate your system in relatively high excitation energy. But still, a lot of systems that can be populated here can basically only be populated by these means. The other way to do is to do transfer of particles, where basically you take an heavy ion and you shoot on a target, and you will exchange some particles. And you will look at this system, and eventually you get some information on how it was populated. You will have also electromagnetic excitation, and this I will go into the details also for those two cases. And beta delayed fission will not be treated here, but beta delayed fission is basically you produce a system, it will decay, and it will decay to a state that will fission. So it has some advantage, because most likely the beta decay goes to relatively low excitation energy, and you will populate your system in relatively low excitation energy, and you can look at the fission modes. So let's first maybe make a quick point on this transfer induced in direct kinematics. So basically you take a heavy ion accelerator. So here it's from a Japanese colleague in the AEA, where you use an oxygen beam and you shoot on a thorium target. So here you will make different reactions, and basically imagine you are the Coulomb-Barry energies, so you can make a lot of reactions. I mean, a lot of channels are opened. But if you use a smart detector here, typically annular silicon detector, you can basically, by correlating the energy loss and the total energy, separate what were the recoil here coming from you have a two-body reaction, so you measure one of the recoil, most likely the light one, which looks like oxygen, and you see that all the channels here are open. But by measuring this here, first you know what has occurred, what was the system that was produced. I will make just a point afterwards on some question about this. And the second point is that you can measure the excitation energy of the system based on two-body kinematics. So just like billiard balls, no? Basically you can reconstruct the excitation energy of the system. So if you reconstruct the excitation energy of the system here, so this is the excitation energy of the system, and here the fission probability. So you measure your system here, you say in how many of those nuclei measured here, I saw at the same time fission fragments that were measured in here an array of, let's say, multi-wire chambers. So basically you measure the position and the time of flight. And one interesting thing, it's related to what I think Patrick showed yesterday about the fission chance. No? Basically here, we are not, let's say, nature is choosing for us where we are populating. No? You have the reaction occurs, you have some selection rules, you have some energetics, you have some states that are able to be populated, but basically you don't populate at a given energy. You populate a range of energies. And you can see that here you can also go beyond, of course, the neutron evaporation, and you can get your first chance fission, second chance fission, and so on and so on. So it has some advantage, because here now you can measure for all those systems. So imagine, it's only one experiment of a week, and here you can measure a lot of systems as a function of excitation energy, and you get the mass. So this is also very interesting, because now you can look at the effect of how, when you increase the excitation energy of your system, how your mass distribution are changing, how you are more or less sensitive to the structural effects. So this is one thing that is quite impressive is those measurements. And here, the main point is that they manage, here is this thorium, but you can do also on curium targets and populate a lot of systems. And here you get all this information from this, let's say, in one experiment. So maybe, yeah, I think here it will fit in the good timing, yes. So the next step I want to do before making the break is that most of the things I showed here are basically, we are measuring mass distributions. No? So there was a lot of efforts to say, okay, let's go to the proper degrees of freedom. No? Because we measure the mass, but the good degrees of freedom of nuclei are clearly the neutrons and protons. No? So experimentally it was complicated to do this. And this is now what has been tried also to see how we can get this information as a function of the good degrees of freedom, which are the neutrons and the protons. So there was an attempt for a long time. So one good try, and something that is also very difficult, but it's a good way to go, is that you can use the gamma rays that are emitted here to tag what are the fission fragments that were populated. Because luckily, gamma rays are kind of characteristic of the nuclei. Sometimes we are bad luck. Two gamma rays can be in two different systems, but okay, imagine now you do several coincidences between the probability to have a gamma coincidence is relatively small to have the same system populated. So then you can use it as a tagger of your ions, and you can try to get back from knowing the efficiencies to get to the yields, to the probability to populate this system, this fissioning system. So there are several systems that are going on and did this for quite a long time. A lot of challenge came from the background because you have the beta decay afterwards, which is also emitting gamma rays. You have to separate the beta decay from the fission. So a lot of developments were made to do tagging by a fission chamber. By using the digital electronics today, we can measure continuously, separate, do subtraction from the let's say decay, which is on the longer time scales. You do high-fold analysis by doing coincidence. You select better and better, but still gamma rays are, I love gamma rays, but they are not always so nice to us. Because you see, every scheme is different. So to be sure that we are able to know what is the yield, you need to know first all the feeding. You have to account for all the feeding. So of course, years after years, we know better the gamma rays, we know better the schemes. There are isomers that can also make some effects. Also, the question of feeding the ground state directly is also a question. So there are some parts, there are some kind of the question that comes into it. But this is, for a very long time, one of the only way to get to this. Okay, so here I highlight some recent results and also some work that was done here to highlight all the, let's say, challenge to account for their yields for different selected isotopes. And you see that depending on the way you analyze, there is a lot of challenge, a lot of work, but like when you need to correct for the velocities, at some point there is no free lunch. You have to work very hard, and at some point you need to get back to get your yields. But here you are really depending on how the fission has occurred. There are some other aspects which are interesting in the gamma rays, that you get some information on how you populated your system in terms of spin, which I will not enter into today. The last point before the break was also the pioneering measurements, and also that were going on, that now you don't measure the velocities, but you want to based on the rigidity. So you have now magnets, you use the rigidity, magnetic rigidity or electric rigidity of your ions to basically get to the, I don't have the formula, sorry, but basically you separate using magnetic elements based on the rigidity of your ions. And then you can measure the mass very precisely also, even more precisely than most of the things we can do. Yes? Rigidity, this is the, how to formulate this? Yeah, I should have put the formula, but the formula will come later. But basically, so you imagine your ion in your ion, which is characterized by mass and a charge state, imagine. Basically, this is the deflection that you have in, for example, a magnetic field. Okay, so this is basically related to the field that you are applying, and this is the deviation that you will have. Okay, so and basically the rigidity is related to the mass over charge ratio and the velocity. Okay? So basically by having this, you are able to get back to a mass in high precision way. If you now add some measurements of the energy, you can also try to see by the energy loss. So imagine here you have an energy loss formula. Basically you can get some idea of what is the charge of the ion. But you have to remember that in this case, it was also done in ELN, so basically they are neutron induced. Your ions are basically velocities of 1 centimeter per nanosecond. So they are very slow, and the distribution of the charge state is very large. But still it was very interesting, because here, for the first time, you basically get relatively consistent way, not depending on the level scheme or something like that, a measurement of the charge until basically z equal to 40. Okay, this is the limit. So basically you cover some part of the fission distribution. Okay, so maybe just before the break, I just want to show you this. This is the nightmare of the fission fragment measurers. So this is the atomic charge. There are calculations based on some parametrization, but the idea is basically this is the atomic charge as a function of the velocity of an ion. Okay? You see that when you are very fast, your ions are fully stripped. Basically, the charge state, there is no charge state distribution. You have basically removed you remove the electrons. As soon as you slow down, so here is 20 centimeter per nano. Here, 1 centimeter per nano, you remember I told you, this is basically where you are with the fission source, spontaneous source. So when you go down, you start to have a distribution of this charge state. And the problem is that what you measure is not the Z, but the charge state distribution and the equilibration of these charge states. And basically here, your intrinsic resolution will start now to get worse and worse, because intrinsically you have fluctuations when you are losing in the matter. And this is what we are trying to fight, and what I will show in the second part of the talk, how we try to attack this by moving from 1 centimeter here to slightly higher or much higher, and to get to, for example, better Z resolution. This will be for the Z part. And at the same time, you gain some other things because you can also measure the mass. Okay?
Great, thank you. We'll take a mini break. Any questions before that?
So you were mentioning that you use a velocity approximation when you calculate masses using the 2E2B technique. And I wonder what implies this velocity approximation? Does the neutron emission happen isotropically to assume that the velocities before and after are approximately
same? Yes, that's basically the same.
Okay, yeah. And how accurate is this approximation in an event-by-event basis analysis of the data?
Can I answer precisely to this? I'm not sure I have the answer to this. I mean, experimentally, I don't know if we can say how different it is, but I'm not really the most expert. I'm sure here you will have more experts that can answer this, but I don't want to say wrong things, so I will just take a few minutes to think or to ask.
Maybe I can say.
Yes, maybe you can do.
Yes, on an event-by-event basis, the neutrons are going to be emitted focused with the fragment distribution, right? And depending on their energy, they are going to be more focused than low-energy neutrons. So there is an impact on this, and it's a tricky correction to make. So, good question.
Mm-hmm.
So, in order to do the gamma ray spectroscopy, you would need to know the characteristics of gamma rays and like the branching ratios, presumably. Where do you get those from?
So there are. I mean, you have all the databases of the structure, which is the ENSDF. Basically, you have a lot. I mean, already a lot, and I would say every day you have new. Isomers. I mean, in the last decades there was a lot of new spectroscopy coming. Basically from fragmentation facilities where you go slightly far, because the point is that you have what you can get from the fission fragment. I mean, there are a lot of spectroscopy fission fragment. I mean, it was from the 70s you did the spectroscopy of the fission fragments. You have a lot of information, but you are biased by your system. So what you get from information is what you know already. What you want is to get the information from a different way, either from you produce by fragmentation and you get some isomer that was there. So this you need really to combine it. So these databases are existing, and you basically you collect them, you put them in the way you are extracting your level scheme. So really you have to do nuclei by nuclei. You extract the intensity that you measure. You extract from any side feeders you need to subtract. And you need to, let's say, imagine you have an isomer and your system is basically measuring on, let's say, 10 microsecond time. If you have an isomer of 200 microseconds, basically you have to account for this. So there are many corrections there. So this is, so it can be either done by simulating a fission and say how your system will have a good response to it. So this is a way to do. Or you do it more really based on the data. But clearly, I mean, I will show you at the end, there are sometimes some problems. And especially because the structure, I mean, the nuclei, the gamma ray spectroscopy depend heavily on the structure of the nuclei. When you have a good rotator system with a lot of gamma rays, first it's easy because they emit a lot of gamma rays, the efficiency to detect them is high. When you populate a very close shell nuclei with high-lying first excited states with low multiplicity, and then it makes a bias because the response of your system is different. And I mean, not even discussing the absolute limiting factor, which is the feeding of ground state directly. But it's not so large, but it depends what you are targeting. If it is 1% precision, like we discussed yesterday, 1% feeding of the ground state is not excluding.
Thank you.
Any more questions, or we take the break, and if you have other questions, we can grab them. Okay, mini break now. Thank you.
One announcement. Some of you received an email today about badging. Please read it carefully and bring your documents for the lunch through tomorrow.
And a quick second announcement. We have this practical session later today. This requires large files. And so if you haven't downloaded everything yet, please try to do it maybe here, maybe when you are at your hotel or wherever. But and another option is Keegan has some flash drives, and if you want to download them from there, feel free. It's more than 500 megabytes, so we need to the internet. Our internet might not work. So if anyone wants, Keegan has a flash drive. Thank you. Sorry.
Yes. So second part. So I recall this slide. So basically, in the second part, I will try to show what we can get by using heavy ion reaction studies for getting properties of the fragments, and what are the, let's say, new observables we can get by benefiting from the fact that we are making reactions, and in particular, how we benefit from the inverse kinematics. So basically the idea is that when we make a reaction, so I mean either you do normal kinematics, basically you can replace this deuteron by a neutron, but basically you bring your nuclei, you do a reactions, basically your target nuclei is barely affected, not moving much, you create your nuclei, it will evolve fission, but it's almost at rest. So basically if you look at basically these small vectors, the velocities you are measuring are, I mean, everything is emitted at rest, so it's nice because you can measure back to back, you don't have to. But at some point, first one of the problems is that if you're in a sample material, between what you produce going one way or the other way, you have different corrections. There are different aspects that are a bit challenging. And the most challenging part is the identification of the charge. Because you are really getting with low recoiling ions, so we get back to our initial problems. I mean, fission is a lot of energy, but not enough. So you have limited mass identification. So this is typically, imagine you have an ionization chamber filled with some gas, isobutane or something like that, at pressure, some tens of millibars. And this is typically what you will measure in mega electron volt in energy. So you have 100, let's say 100 MeV available, something like that. And if you look at the correlation between the energy loss and the total energy, you get those, in principle, some separation should come here proportional to the E. But this is basically limited for the light fragments. You can get something, can be challenging depending on how slow you are. But there is no way that you will ever get anything on the heavy fragments because they are in what we can call Bragg regime, is that the energy loss is not anymore, there is not anymore a proportionality between the energy loss and the total energy that will allow you to extract the charge. So to go around with this, okay, let's speed up the ions, no? I mean, fission is a good accelerator, but not good enough for what we want to do. So the idea is now, let's imagine now you come with already a lot of energy. So you do an inverse kinematic, you take a heavy nuclei that will go on the light nuclei. And basically benefiting from the energy of the frame of the nuclei, basically, you will just boost everybody using this. And then you benefit from this extra energy, which has nothing to do from the physics, I mean from the physics of the fission. It's just an accelerator for your ions there. Of course, if you do this, you cannot do same reactions. You have to also account and get some, all the inverse kinematic reactions are surrogate reactions. But if you do this, now your fragments have much higher velocities in the laboratory frame. And then you can basically get a, let's say, better identification or even an excellent identification if you go really fast. Okay? So this is typically what you get if you go to Coulomb-Barry energies, and this will be one of the two cases I will discuss. And you can even go to relativistic energies, this I will show also. So here you go beyond 3 centimeters per nanosecond. Maybe I will allow myself to get back. So you see, you're going from here where everybody is completely mixed. So this is from different charge. Huh? Maybe I forgot to tell this, but this is for the Z equal 90. So here, Z equals 30, so you have different distribution, but basically here you see that between Z equal 90 and Z equal 30, you will have the same distribution. And this is what is Bragg. Basically everybody is unresolved. So we want to go as much as possible. So at 3 centimeters per nano, you can start to get something good. Maybe not for the 90, but at least until 60 or 70, you can do something. So this is where we are placing ourselves. And you can get these correlations, and every line here is associated to a different Z. And you see you have the light fragments or the heavy fragments. So you can get now complete measurement for the whole fission, let's say, charge distribution. So let's start also from maybe a historic point of view, but I mean, it's not so far away, no? So the pioneering work of this was to use relativistic beams at GSI. So to use a uranium beam at 1 GeV per nucleon, so this is really fast. You fragment your uranium beam, or you can get it through, but let's imagine now, you fragment your uranium beam. You will make different products from fragmentation. You use a separator here, which was basically FRS. So you will separate the ions. By measuring basically energy and time of flight, you can get an identification. So here it is in positions, but I will show you later an identification. And you make basically here a cocktail beam of radioactive ion beam that you can use afterwards to make secondary reactions. This is what was obtained for proactinium in this case. But basically afterwards, these nuclei that you have produced here, you send on a heavy target, typically imagine lead, and you will make electromagnetic excitation of this ion, so high enough so that it fissions. Then afterwards it will fission. You can get here, let's say, ionization chamber, and you will measure the charge of the ions. So the goal here was to say, okay, we made a lot of measurements in mass, but we don't have charge. So the goal here was really focused on the charge. So what happens is that you come here, you make your reactions on an active target. It's not really important here, but basically you make different reactions and you can tag the reactions. And then afterwards here you have what's called the music chamber, where you measure the energy loss. And this is what you measure basically in terms of charge. So here you really resolve the charge. So this is the charge distribution. I think this one I forgot for which system it is, I'm sorry. But basically, the second aspect of this is that you can measure in one experiment 70 systems. Okay? So this is the charge distribution as a function of the neutron number and proton number of the fissioning system. So this is a very impressive work because you can now look in charge, not in mass, how the, let's say, fission distribution changed as a function of the composition. And this was very important reason because you can see that you have a transition here between an asymmetric distribution towards more symmetrics. And also by doing this, you can now make systematic analysis of the position, for example, of the heavy peak. You remember this picture that I showed you about neutrons, about neutron-induced system? Yeah, you have the question here.
How do we know which system we've populated?
Yeah, sorry, I was quick on this. So basically you make uranium here, you make a reaction of fragmentation here. So basically here you have a magnetic spectrometer or separator. So you again one more time measure the rigidity. So you measure the mass, and in addition to this you can also measure the Z by an energy loss. And then basically you have a unique identification event by event of your system. And you can get a PID plot basically for this. You make a selection on this, and then you make, it's like you're making the coincidence of this, identify incoming ions, and then you make them as secondary reaction. I'm sorry, I was too quick on this. It's good that you asked the question. Yeah.
I have a question. How you determine the excitation energy of these?
We'll come to this in a minute. Yeah, was this my next slide? Yes, this was my next slide, so I can come to this. So just to finish on this, now basically you have by this measurement kind of a demonstration that the stabilization that was seen in mass is related to the charge and not to the mass. Okay? And this was measured over a wide range of systems, and this was a very important result. And the second part is that there is a transition between an asymmetric to a symmetric, so that the structural aspects are basically the effects are changing from one to another. Okay, I will continue and see if it continues. Okay, yeah, it's much better. So coming to the excitation energy. So yeah, I will start with this, and then I will show what is now the future of this, because this was some time back. But basically, what you are using as an excitation, let's say vector, is that you are using electromagnetic excitation, and this is what is the calculated excitation energy profile. So of course, it is not absolutely defined, and it is calculated and not measured. Okay, so you have this effect. So basically, the range of energies is between 5 and 25 MeV, with, let's say, kind of maximum here. So this is what you get. So, of course, this is, and in the end of the lecture, I will show you what we are also doing today now to get to this measurement of precisely of the excitation energy. So, you see, it's always, I think, measuring fission fragments is a matter of compromise all the time. So, it's one of the compromises that here, you get this. You get this in one shot in a consistent manner because you are not too much biased by what you do. The excitation of the system is basically not too much changing from there to there, and you can make direct comparison in this measurement. So now it was only the charge. So now the follow-up of those measurements is what were the SOFIA experiments. So basically, the idea is the same. You produce your radioactive ion beams, a cocktail of radioactive ion beams. But now, in addition to measuring only the Z, you want to get the mass, no? Why not to get everything? No? So for this, you need to get a spectrometer, so which is it was the Aladdin spectrometer, and that now is the GLAD magnet in the R3B collaboration. And basically here you have a large magnet, very large magnet. So here I show you a picture. So unfortunately no postdoc at scale, like yesterday, but basically it's really big. I would say that this is you have here the scale basically they are meter size magnets. And here by measuring the magnetic rigidity, one more time, basically the mass over charge and some velocity, you get access to the mass. So just to show you those cocktail beams. So basically this is typically what you get as a secondary beams. So they are here just to show you, this is the mass over charge ratio as a function of the charge. So this is determined by energy loss, and this is determined by the magnetic rigidity. So you see here you can separate every incoming ions. Afterward you make a selection of this, and you make you look at your selection. This AO charge is not measured in the Aladdin. Just to be clear, it's measured in the separator, in the first part. Here, this is for this part. Okay. So once you select on this, afterwards now you can look at what is obtained in terms of charge here and mass. And here are the complete distributions that are obtained. Okay. Basically, now you are really high energy. So you remember my plot of charge state. So basically, the charge state is most likely to be the charge of the ion. So A over Q is basically A over Z. So you have A over Q. You measure Z, so you have A. Okay. And these are the mass distribution that are obtained here in the case of uranium-236. And this is the charge distribution measured here in the same system. So here, I think this is the best resolution that you can ever get in terms of identification of charge here because of the energy. Okay? So this is, you have to see that you are measuring, you resolve uniquely every charge. So now you imagine, you fold this by the fact that you have a large amount of nuclei that can come. And for every system, you get those charge distribution in a similar, let's say, entrant channel. Okay? So I think today I will basically mostly focus on the yields, because this is one of the goals also of the SOFIA collaboration, is basically to get those yields precisely. And so there are the yields here for the uranium-236, let's say, gamma fission, okay, as a function of nuclear charge. And here are the typical uncertainties that you can get associated to those measurements. So what are the uncertainties here? There are not that many, some. So in terms of statistics, this is relatively small. The statistics is, here you see that you are dominated on where you are weakly populated, you are dominated by the statistics. The systematic errors, so it's quite very well forward focused. So in terms of transmission and acceptance of your nuclei, you are not too much biasing your distribution. One thing that you have to account for is that you are making electromagnetic excitation, but you're still doing nuclear reactions. Okay? So you have to subtract the nuclear reaction from this. And this you can do by using different targets. So you can make reaction on lead or reaction on carbon, and basically you can make subtraction on this. And this is part of the systematic error. But here, you really reach some level of precision, which is now, comparable to some of the things that we discussed on the other days. So basically here, this is in %. Okay, so we are really reaching this kind of levels. Here you see the yield distribution, the % in % here, compared to measurements done, for example, for cumulative yields. And you see that, okay, so in some cases it works relatively well, some cases it deviates. So this we know is it's very challenging to get from the cumulative that you need to know a lot of information to get back to these independent yields. But basically the message here is that here you have a complete measurements that are available. Of course, it's not a neutron-induced reaction, but the energy range is also compatible to some measurements can be done by neutrons. So this is, here you see, it was taken with energy of neutrons of 8 MeV, which is the kind of middle of the distribution. So this is one of the messages I think here is to say that basically you know those things can be compared and gain from each other and get kind of combined analysis of those informations. Okay? One thing that I'm not at all discussing is that I've not told, but I mean, as we are a relatively stick beam, the system is so focused, you know, my two vectors now, they are really pointing towards so you can measure the two fragments at the same time. So now you can play on the conservation of the mass, conservation of the charge. There are a lot of things that you can look at. And I'm not showing here because I was thinking I would be a bit late, but I'm quite in time. But maybe we can discuss this. But you can measure the total neutron evaporation basically here because you measure the two fragments, their mass, their charge, and what is not there between the difference and the system you had at the beginning is what you have somehow lost on the way. So let's maybe move on to the next point. So now you were discussing excitation energy. So one way now is to, okay, we get the most favorable case because we were wanting really to get Z. So you say you boost it. But at some point, of course, you cannot get everything at the same time. So now let's do an intermediate step. Let's go back to Coulomb energies. So this is basically getting 3 centimeters per nanosecond, which is our cutoff for getting some Z identification. We go to the minimum because there the reactions we can do. I mean, we can populate the system in an excitation energy by using what I showed in the direct kinematics. You remember the work from our Japanese colleagues? You make transfer reactions, you make the excitation energy, and you try to master the entrance channel. And at the same time, get the complete identification of the fragments, not to lose on the way. So this is what is done at VAMOS, basically, in addition to be complementary to SOFIA, because SOFIA, you remember, you use fragmentation. So basically, you remove nucleons from your incoming beams. So all the nuclei will be lighter, so starting from uranium, only below uranium. By here being at Coulomb barrier energies, we can make reaction that is adding nucleons, so we can get heavier systems than uranium. So there is this kind of complementarity of the systems that you can populate. So basically, you take a uranium beam at 6 MeV per nucleon, you send on the light target, carbon or beryllium, and you make some reactions. So you can do fusion. So there you have nothing that goes out because everything goes straight and then eventually fission, most likely at relatively high excitation energy. Or you make some reactions and then the target-like nuclei, so can be elastic, can be one neutron transfer, one proton transfer, can be detected in a silicon detector surrounding the target. Basically, it's a delta E detector. So I have a picture here. So Fanny showed this plot yesterday already, and you'll see today a lot of this plot. Basically, here you have the target. You make reactions. The target-like nuclei gets detected in the silicon detector, and by delta E correlation, we can select the nuclei that were populated. Also, by some kind of luck of kinematics, the fission fragments, the system that is populated when it fissions, the fission fragments still get into some cone, which is typically like 30 degrees. So luckily, it does not go at the same place. Otherwise, it will just be impossible to detect at the same time the fission fragments and the light nuclei, and your system will also the detecting system will not survive. So if we now measure the mass, the charge, the energy, and the angle of the recalling ion, we can get back by using two-body kinematics to the excitation energy of these systems. So this is typically what is shown here. So this is to say in 10 years back, it was measured like these first measurements of this excitation energy in inverse kinematics. So here you have excitation energy measured here. Of typically you see this is 0, this is 20 MeV, and here this is the barrier of the system. So this is a 2 proton transfer, so plutonium 240, and this is, we are populating around the barrier. So by basically measuring what has fission from what has not fission, we can get to a fission probability, okay, that you can compare afterwards, either by neutron induced or other surrogate methods. So this is basically one way to now get some information of the excitation energy. So of course here, you have some limitation of the resolution you can get here. So in this case, in the case of SPIDER, we have like 3 MeV, something 2 to 3 MeV excitation energy resolution. But you will see today, there are new results from an updated system where we have almost reduced by a factor of 3, so getting towards below 1 MeV excitation energy resolution, okay? So this is the entrance channel. But now, of course, we will correlate this naturally to what we see in the exit channel, which is the fissioning system. So here you have VAMOS, which is a spectrometer, basically with these related equipments. So the challenge here is that we are still low excitation energy. Huh? So in between 4 and 8 MeV per nucleon, so ions, we are a vacuum, but we don't want to put too much foils. So we really have to minimize all the dead layers there. So the detection systems are made of multi-wire chambers and ionization chamber. And the idea is basically by using these simple, let's say, equations, but not with slightly more complicated things here, but basically you measure one more time magnetic rigidity, you get back to the mass over charge, your ionization chamber gets you delta E or basically a Z information, and by measuring the total energy, now you get back to the total identification. What I've not shown here is that we have a lot of charge states because we are not too high in energy, and that's why a good total energy measurement is what is allowing us to get back to mass over charge. Here is measured by the rigidity. Here has disappeared, but here Q is the charge state. So we are measuring the charge state, and every blob here, you have lines like this, they are the mass. Okay? And this is the correlation between the energy loss and the total energy, and every line is a Z. So by doing this, you basically get the let's say, fission fragments distributions that you can see here, not corrected for acceptance. Okay, so this is the charge here and the mass. And typical resolutions are 1.3% in Z, or let's say typical best, 1.3%, and here 10 to the, let's say, 10 to the minus 3. Okay. So afterwards, of course, now you want to get back to the yield, so you have to account for the acceptance, to the charge state distributions, because you have distribution of charge state that can be relatively wide. And now a magnetic spectrometer is in mass over charge distribution. So basically by having this, now you have to correct and to account for this, and this is part of the limitation of those systems, is that we have now to work hard to be sure that we are not biasing the data. And this is, but thanks to the large acceptance of the spectrometer, we have ways to select center of mass, let's say angles, where the system is, we are able to have non-biased fission yields. Okay? And this is what we can get, for example, here in this case of neptunium, at 7.5 MeV measured by SPIDER. Okay, so let's go one more step. So having complete yields, what does it mean? So this is what, it's another view of what Fanny showed yesterday, but basically here for every element, you have the charge distribution, and they are, let's say, it's not only for even nuclei, they are all, okay? So this is what we get. And just to highlight, that it's very important to have those complementary measurements, because in the colors here is what was measured by gamma ray, okay? So this one is for uranium-239, okay? So I will not detail how we may get this measurement, but basically imagine we do a neutron transfer, uranium-238, neutron transfer, and you get those yields. So you see that, okay, first it's not measured everywhere, so now you do it in kind of systematic way. But now, just to get back to what I showed, it's exactly this. Yeah, oui.
On the previous slide, the normalization, it's normalized on what? Because you have a 1.
No, this is in percent. It's not 1. It's normalized to 200. Okay? So in the way you are normalizing is basically you normalize your yields to 200, which is the way it is done. So this is 1% log scale. So of course, usually the peaking part is like 6 or 8% or something like that. So basically, you will have everything in this peaking part. Okay. So yeah, it's log. Huh? So you really see that you are going to very small yield, let's say fraction. No? This is where we are able to get. Huh? Okay. So this is, it's really, should not be taken as a blame. Huh? It's really to show that it's very, very challenging. And here you see the case of tin. Tin is not made just for randomly. Those nuclei that are closed shell nuclei, they are really challenging for getting those measurements because the structure is affecting dramatically the way we are able to, let's say, account for their decay. And basically there was those two measurements. There was a long debate about this, but independently of this, now they are neutron induced, but such a difference is nothing to come from the reaction mechanism. It's clearly coming from the way we are able to extract those yields. And I mean, what I find nice is that basically we have these different measurements. Now we can go into the real details how they are slightly different, but when you have big differences, we have really to use it as a driver for our understanding how our experimental methods are, let's say, how we improve our experimental methods and control on the experimental methods. From what it seems, but maybe somebody in the audience, I don't know, but basically the point is that there is a big challenge about accounting for the side feedings. No? This is the main challenge. Okay, so what we get out of this? So basically you have a set of revisited observables. Basically you have now the charge, you have the mass, so you can get, let's say, charge yields, isotonic yields, and you can look now at the different systems that are populated. So here in a typical experiment, you will populate several systems. Maybe I just go back to this just to show you. So basically every line here is a system. Of course, for the light here, it's more complicated how you get back to the system, but basically here, you have the different carbon systems that are different uranium systems. Here, if you do proton transfer, two proton transfer, and eventually here you have two lines, lithium or alphas, or even if you populate beryllium 8, you get then it breaks into two alphas, so you have all these different systems that you are populating. So basically in an experiment, you get this different yield distribution, and you can compare. Of course, we do not choose, like an accelerator, where we go. The physics decide where the excitation energy goes. So you get some excitation energy distribution with some control, more or less, depending on the detection system we have. But basically, you have here range from going from 7 eV to 46 MeV. This is fusion fission, huh? Californium 250. Okay? And you see that there are different features. First, this stabilization is still there. No reason that it changed. But basically, you can see also that the asymmetry is also slowly when you increase in excitation energy. So you also have this changing between asymmetric to more symmetric fission when you increase the excitation energy. So it's another feature. And even if you go to relatively high excitation energy, you are not completely fully symmetric, which is also an interesting part. The other part is that now if you look at the staggering here, so we have this even odd effect, which is also known for some time, but those kind of data can also bring some information on the even odd effect, and I think Diego will speak about it this afternoon. Second part is now you have those different yields. Now you can try to combine them, no? So you can look at, let's say, the neutron content of the fragments when they are, what is the neutron content for those different systems? So this is the average neutron number as a function of the Z. So basically how we do this, we have the independent yields and you extract the average neutron content at a given Z. It's just summing of the yields, you just average by the relative importance. And the interesting part of this thing is that so sawtooth, in principle, we see a lot in fission, in neutrons, most of the time. And they are most of the time revealing some information about, let's say, structure, excitation energy. But here you can see that basically here you have this neutron content has a very strong effect here. And also what I want to point is that those yields here at Z equal to 50 are basically nothing. Huh? If we look at it at this distribution, we have no chance to see this. Huh? Everything is hidden because it's very weakly populated. But now the way they are populated is very different from what is on the side. And this is really associated, of course, to structural effects, and that are also vanishing when you go away higher in excitation energy. Excitation energy basically go tuk like this, and we are fusion fission. Basically, you have almost, let's say, liquid drop behavior, where everything is equilibrated in terms of N over Z ratio. Yeah, this would be perfect. Okay, so let me go one step. It's basically maybe just to introduce the talk of Diego, but it's more than this, is that I talked to you about 2V methods at the beginning based on, let's say, simple measurements. But now you can combine this with all the knowledge we have of the of the isotopic information. And this is because of Coulomb barrier energies. And if I get back to my sketch here, if you are not too fast, if you measure the angles and the velocity, you can get back to pre-neutron evaporation and eventually get some information on the neutron evaporation. So this is where we are now. And this is only possible because of the Coulomb barrier energies. So there is a kind of luck sometimes in the kinematics, but this is what can be done. So this was done in this paper by measuring only one fragment and making some assumptions. But now we are wanting to go to measuring 2 fragments. And then you will release some of the assumption that is being done. Okay? So maybe let me conclude. I will have one slide of summary, which is, I think, quite general. It's not that I want to go through this, but what I just wanted to highlight is that there are really challenging experiments because we are manipulating nuclei that are stopping in nothing, and that basically we are hardly having their properties, either in energies or velocities. But still, I mean, a lot of measurements were done, and we're able to attack these challenges and get quite a lot of precise, first, experimental techniques. There have developments of methods for accounting for the energy loss. It's very impressive all what was done over the years. And now, based on this, now we have a lot of data which is associated to this with high quality. And the new developments that are going on now, either by using the 2E, 2V methods, or gamma ray multiplicities, now we have new ways of correlating those observables. And I think this is where we are now in correlating this. And this is also what is being done in the inverse kinematics methods. Basically, now we can access different systems and get correlated observables. And we are constraining somehow what are what is trying to occur basically when the nuclei fission. And just as an outlook, I mean, 85 years of studies, but we have not yet finished what we want to do, because in the last decades, I would say the last 20 to 30 years, the main change now has occurred in bringing really new observables that are now, I think, going along with what was measured before and all the other measurements, and getting them correlated is really, really an important task that we have to do, both by improving the way we master the uncertainties, and both, let's say, aspects of fundamental research, going back to your initial question, is that it's both from the data we want, that we can contribute, but also from the fundamental research, knowing what has happened. And this is really, both those things are contributing into this. And I've not at all discussed, but I mean, I discussed a lot about the actinides here, but there are a lot of work that is going on, and there will be a lot of presentation today and tomorrow on some of the work that has been done here. And by changing the systems, we also can probe differently the structural effects that are driving the fission. And I think all those things are reflecting in a lot of, let's say, ongoing activities and new measurements, new opportunities using the radioactive beams, and both in Europe and in the US. I think it was shown for Argon, FRIB with the HRS. I know that there are some discussion about how to go with this. So I think there's a long and bright future for the measurements of fission fragment properties. Thank you.
Thank you. Time for questions.
Thanks, I think I've learned a lot. You mentioned that all these inverse kinematic experiments are surrogate reactions. So I'm wondering, do you have a sense for how the different observables that you get depend on the entrance channel, the reaction that you do, like the yields versus the charge distributions versus the neutron multiplicities? How do each of these depend on the entrance channel?
They definitively depend on the entrance channel. I think Diego this afternoon will show something specifically on this, on one case. I think it's an opportunity in some way. The main issue I would say is that in these inverse kinematic reactions, I mean, basically it's not that we populate one state, we populate the distribution of states. So now if you want to unfold this, you have already to master also your, let's say, the way you are populating. It will have an effect, because definitely what Patrick showed yesterday, basically the angular momentum you will populate, and so in this way it will affect. But we see also that sometimes it does not affect that much, because when you look at the yields, some of the yields, they are barely affected by this. And now you have to depend on the observables that you will have. So the question of the angular momentum is quite hot on this question, is that how do the angular momentum of the fragments is changing or not depending on the entrance channel, not entrance channel. So I think in this way you can bring some measurement where you measure something. That's why measuring properly the entrance channel, at least in excitation energy, but I would dream to measure the spin of my entrance channel, but we are not yet there, I think. So it's clear it has to depend. Now, how much is it within the precision of what we are measuring today? In some cases, it looks not, because the yields are really very close.
I'm curious regarding the heavy fragment peak stays constant as you fission different elements, different masses, and is this a cutoff in the proton number or the mass number? Is it due to the thin structure that you end up getting at least thin? And is it understood? Or
yeah, I think it is understood now. Now it's clearly understood. So basically, the point is that I did not want it that in this lecture to go into this question of which structural effects are affecting what. But basically here, and this is what is shown here. In fact, in this way, I think this is nice because it highlights how you go. So you see, you have this stabilization in Z. Okay. So somehow what is understood today is that you have some shell effects. So basically you have some correlation energy that is favoring your system to go there, to make it in a simple manner. So now what can create correlation in your system? You can get extra stability because of your sphericity, but you can also have some level of deformation that is also stabilizing the system. And today this is understood as basically a stabilization due to octupolar correlations. This is the way how it is. So basically, some of your nuclei here have octupolar, let's say, correlation that are stabilizing your system, and this is basically in charge, but also in neutron number. So basically, here you have what you see is that you have some region where your nuclei are favored to go. This is how it is understood, and basically this can be seen in charge because it's mostly driven by the charge. Now, if you change completely your system composition, you go towards your, let's say, neutron deficient system. Now you can go away from this. Specific shell effect, but you can say, okay, I keep the same possibility in terms of neutron numbers, but I completely discard the possibility of charge number because the total charge available does not allow me to go there. And then you can see whether it is the protons or the neutrons that are remaining, or if they are both, let's say, coherently acting. And this is how, by measuring, that's why measuring different isotopes is not a matter, is not a detail. It will be a way to leave the degeneracies basically sometime on what are the structural effects.
Okay, May? Yes?
So I have one question. I get the appeal of measuring neutron multiplicities with fragment masses and subtracting them off to get how many neutrons are emitted. It's always kind of bugged me though. What kind of precision do you think you'll get from mass subtraction for neutron multiplicities when really the evaluations are on the order of 0.5 to 1%?
I don't know today. No. I think it's a good question. It's a good question because basically you are measuring the velocities here. You are getting everything from the velocities, okay? And today, we cannot. Today we don't have from this 2V method. Basically, we don't have mass unit, okay? So we are slightly. I would say like any of those measurements, 3-4 mass units. So this is one limitation, okay? To get it in an isotopic manner. But now, basically, the development of this new, slightly longer time of flight is the aim to go to 1 mass unit there. And if we get there, the day we will get this, I will be very happy because at the same time we get isotopic TKE, isotopic let's say, neutron evaporation. So we get everything. But of course, now we are still limiting by this resolution, and it has some impact there, of course.
Okay, so are we ready for the break? I guess so. Okay. So thank our speaker again.
Sorry, I guess I have a question.